Yeah, so I think thank you so much for the kind words, and I think let's just go forward with the optimization and its application to ads. And yeah, so I think the major agenda today is that like we look at the mathematical programming or the commutator optimization that we have, and how we can actually use that to solve a bunch of problems in ads. The primary focus today is to actually develop a motivation as to why we can use optimization techniques, number one, and number two, use Google OR tools to like handle a couple of problems that we discussed today. So that's the whole agenda. And the success of this session would be like if I could actually basically motivate people to start using those OR tools and like start thinking in terms of like optimization. One thing I just want to call out that mathematical optimization, or sorry, mathematical programming or commutator optimization, as it says, it's a very vast field, and we won't be able to cover up even a bit of it in this session. But this is more like to whet the appetite of people. So I hope this screen is the fonts and all those things visible. Cool. Yeah. So let's just go on to a simple example just to motivate a typical scenario. So what we want to do is that like let's assume I am an ad channel, and like I have 3 channels available to me, and I can actually receive clicks across those channels. I just call them ABC. This could be like Google, this could be like Facebook, and so on. And also I have is things like age range. So if you look at this table, right? So on the rows are the age range, and what it tells you that, like for example, column like the cell which is corresponding to column A and the age range 18, 25, which says 10. It says that like for generating clicks on this channel, I need 10 impressions from 18 to 25 range. Now the question that we want to ask is that what is the maximum number of clicks that we can achieve provided we have this kind of data. Now this is one of the key problem for bunch of people, right? Bunch of folks, agencies, ad agencies, and so on, who are advertising across multiple channels, and this is a key problem for them. So now we want to, as we understand, right, like there are multiple ways we can actually primarily focus only on A and then consume some number of clicks, or we want to do a mix of A, B, and C, and so on. So this is a kind of problem that we talk about in optimization, which is the crux is that like you have some information available and then you want to optimize a certain criteria. So if we talk about like what are the various ways in which this problem could be solved. So I think there are a lot of modeling languages. So there are like AMPL, GAMS, and so on. These are like sort of formal languages which have been devised to pose this previous problem, like whatever this optimization problem is. And similarly, there are a bunch of solvers. So what does it mean between modeling language and solvers? So modeling language is like programming language. They sort of express this mathematical model in terms of like something that computers can understand. And solvers are like sort of like if you think about, like they're actually like machine learning algorithms, or these are algorithms which will optimize it. Like these are ways of taking up this formulation and then coming up with a solution that is optimized for it. And then we have a bunch of solvers for this. Now if you think about it, there's like huge research that has happened in past 50, 100 years, and these are like primarily used across multiple kind of modeling. In fact, just for the sake of this thing, right? So I think in 1940s or 50s, there was work done by economist called as Leontief, who actually further received a Nobel Prize, where he used like bunch of equations to express how does economy work. So such kind of formulations can actually be solved using these solvers. Now, one of the key aspect of this kind of solvers is that like many of them are actually commercial. They're pretty expensive, and like it's not applicable in a lot of day-to-day usages. So that's come the place where we say Google OR toolkit. So OR is basically operations research. And this is a toolkit that is provided by Google and is available like well integrated into Python and so on. And this is the focus of today's talk. It's very easy to install, like you just do pip install OR tools. The advantage of Google OR tools is like multifold. So first thing is that it has bunch of solvers, as we see linear and integer solvers, which are integrated into the software package. That's one of the first advantage. Number two, it's rightly integrated into a Python thing. So like you just do pip install and then you can start solving it through your Jupyter notebook or something like that. That's the second major advantage. Number three, it's free of cost. So if you want to solve a problem in your business use case and you want to just see whether the optimization is actually working or not, you can go ahead and do that through OR toolkit. If you realize that, okay, your problem is really large scale and you need to invest into some the actual commercial solver, then you can actually take a call between Google OR and that's the kind of solver. So it's sort of like the same kind of freemium model that Google has applied elsewhere. Like basically take these things and like you can try this and then go forward. So the simplicity and the way it has been done, that's where I think I picked up Google OR solver to demonstrate today's talk. Now let's just come back to our original problem. So I think let's just not focus on the top part of it right now. Let's just focus on the bottom part of it. And what we are saying is that like we want to figure out this problem, which is like you can generate ad clicks across multiple channels. You have audience coming from multiple age ranges, and then and each age range you have like number of impressions available, which is given by the total, the row total, and so on. And now you want to figure out what's the maximal number of clicks I can generate. So the first thing that comes up to your mind is that how do you even approach this problem? So we need to start thinking about what is the variable here? Like what are we exactly solving in this problem? So in this case, if you look at, right, the row totals, which are like 800K, 500K, 100K, corresponding to age range of 18 to 25, 25 to 35, and greater than 35 respectively, that is a given quantity. So we can't control that. So you can't change the impressions which is possible there, or the opportunity where you can show your ads and so on. So that's not a variable there. Now we look at the other part, right? So what else could be a variable? So if you think about it, in this case, right, if you think about so the number of impressions, like number of the number of participation from each channel, that's one of the variable. So let's assume we denote that how many times you participated in A, B, or C across these channels, like say X0, X1, and X2. So the objective that we have is that we want to maximize this clicks which is being generated by A, B, and C. Now, what are the constraints that we have? So let's assume we have X0 clicks being generated from A. So if that's the case, then it would have taken 10 impressions in the range of 18 to 25, or 15 impressions from range of 25 to 35, of 8 impressions from greater than 35 to generate this click. So this is like one of those things that can happen. So what we have constraints here is that like for every time I pick up a channel of like X0, I need to have like, so that's where the constraint comes. It says that like, if I consume X0 units, so 10 into X0 plus 12 into X1 and 22 into X2, that sum should be equal to 800K or lesser than 800K, like if I don't want to use a complete age range. Similarly, I have things for like 25 to 35 and greater than 35. So if you look at the top, right, what we're trying to say is that like, you can have the quantity X0, X1, and X2 such that these three constraints are satisfied. These are the constraints in terms of the total available things. So whatever is the ideal value of X0, X1, X2 is what is going to maximize the number of clicks. Now, if we just go for a solution to this, like how do we actually solve this problem? So if we think about logically, right, in terms of algorithmically, we would try to do some sort of like either kind of a 3 for loop, which is basically running the X0s into something, or you write a DP or something like that. So that's the typical setting which we are working. Now let's just 1 minute move on to the solution for this. Good. So I think let's just look at this, right? So this is our problem, ad allocation problem that we are looking at it. Now, as we discussed before, right? So we have the objective where we want to maximize the X1 plus X2 plus X0. Now, again, in this case, I just took an addition just for the sake of demonstration, but you can actually have different kind of functions. You can say that maybe there is some second order utility such that X0, the utility from X0 is like twice of X1. Then we say like, okay, X0 plus 2 of X1, because for X1 to be like, for every unit of X1 to be valuable, should have generated like twice or like half of what X0 is generating. So we need to basically make sure that the quantity should be much higher than. So those things can be changed. Like this is just a simple objective. Now let's just come back to how do we actually solve this problem. So I think let's just start with this OR tools. I think this is just a solver that we are picking up. What it tries to say is that like from the tools, we want to pick up a linear solver. Now, if you think about it, is this basically the add allocation problem. So in this case, what we're trying to say is that we have a solver. T is just the name of the solver. Now we have a solver where we want to say that we want to go for a linear program. Now, why we are saying we want to go for linear program? Because in this case, if you look at it, the objective is a linear function. What does it mean by linear function? Because there is no term, which is there's no power. There's no there's no x square. There's no x0 into x1 and so on. So everything, every term of this equation is linear in the variables. So that's why we want to go for a linear program. Now, linear programming has a lot of beautiful properties, and it's like much more tractable. It's much more solvable. And if you go for the if you go to mathematics of it, it's a nice property that the solution lies on a simplex, like basically a convex hull of the potential points which are there. So it has neat computational properties, because of which it's very fast. So we just want to pick up one of the linear solvers. Now what we want to say is that in this notation, right, in this what you call as the OR tool notation, the key thing that we want to do is that we want to first define the variables. So we want to say that I have some variables x. So I say that these x's are basically a number. Like here, I've just arbitrarily put another constraint that like the value of x need to be bounded by between 0 and 100k. So you can have a different number. But what we're trying to say is that like x is basically a vector of numbers. So we say s is like our solver, and we are just adding a numeric variable whose lower bound is 0 and upper bound is 100k. And we just denote it by name, like x of I, x sub of I. And what we're saying, like it's basically a name that we want to represent to, like it's basically to refer that it's like a sub of I, like it's a variable of I that we want to do. And similarly, there is another variable that we define, which is again a numeric variable, which is the pop, which is like summation of these two, all these three. And we say like, since the maximum values of each one of them could be 100k, so I just set it to 300k. So now if you pick up this whole thing, then I want to say add more constraints to it. So in this case, I'm saying that 10 of x, like as we discussed about, is just like the directly mathematical translation there. So we say 10 times x of 0 plus 12 times of x of 1 and 22 times of x of 2 should be less than 800k. So that's my first thing. And similarly, like the second equation and third equation. Finally, I would want to say that like the pop which is there should be sort of that's equal to the summation of these three. So this is because I'm going to ultimately, I want to make sure that I want to maximize pop. So when I'm maximizing that variable, it practically means that I'm actually maximizing x0, x1 plus x2. And then I go ahead and solve it, and I get the solution value. So if I look at it, right, in this case, if I try with this set of numbers where I've actually put these things, and there is no other constraint that is there, so I can just go ahead and solve it. And so basically, here I get the solution. So what it says is that like primarily it's trying to say that the maximum value that you can get for the summation is by like 19,000, close to 20,000. So this is just a numerical error. So 20,000, if that is coming from only picking up bees. So it's basically saying that like you want to maximize, you can maximize the clicks from by actually consuming the maximum quantity from the bee side of things. If we look at, if you just say maybe change these values to say smaller, like say I just change it to say 8 or something.
Rahul, sorry to interrupt. Could you please zoom in a bit?
Pardon?
Can you zoom the screen?
Oh, zoom, 1 minute. Is it good?
Yeah, now it's fine. Thank you.
Any question till this point? Unfortunately, I'm not able to see the chat window.
So far, no questions are posted in the chat session.
Okay, sure. Okay, cool, cool. So I can't share because it's a, how can I share this? This is running on my local host. So I can, shall I just copy the notebook to some place?
So maybe you could download this Jupyter notebook and you can share it via chat session, or you can send it to us. We can share it over.
Okay, so I think there is one question from Rutuja Sanjay, and I think okay, so which is basically like how was the value of 100K decided in third line. So as I said, like this is I just put as I told, like this is just a reasonable constraint I put together. There was nothing in the problem, and I if you don't put it, it's like going to it just what you call as nothing changes there, because ultimately, since it's a constraint problem, the numbers x cannot actually take a negative value. We have say 0, so it's all they're all strictly non-negative numbers. So the addition will be a positive quantity, and it cannot go beyond certain number. So just for the sake of simplicity and like performing this thing, it takes two arguments, and it's like much simpler to give like the maximum limit. That's how I put it. Even if you don't do it mathematically, it's not even required. So if you think about in this maximization, since these are all positive quantities and there is a constraint for and this like x0 x1, these are all positive quantity, everything is positive here, so there exists a limit beyond which this number cannot actually increase. So it will still converge mathematically, it just eases up the thing here. So there's no what you call it, any specific reason, it's just for the simplicity of things. Perfect. I think there's a very good question by Omar Kurban. And I think, yeah, so I think I would want to evaluate on that. So I think that's a very good question. So what he's trying to say is that like, what can we do the sensitivity analysis? Now, a very interesting question comes up is like, what does it mean by sensitivity analysis? So that's the thing is that like, when we say sensitivity, so we have actually got a solution here. Like if you look at, there's a solution that has been generated. The natural question that would come up is that like how sensitive this equation, or like how sensitive or objective is to this solution. Like for example, instead of 19,000, if I would have taken say 20,000 or 21,000 or say something else, is it that like the optimality will get impacted too much? So if the solution is very sensitive, even the neighborhood points to the optimal solution will actually cause the optimization to be become drastically worse than what is the optimal solution. So yes, OR tools do allow us to do that particular kind of optimization. Now, in terms of check its optimality, so the optimality is usually the way this is linear equation is given up here in the thing. This tool is actually, this solver actually returns back the optimal value. And in this case, like it's guaranteed because it's guaranteed by the way simplex algorithm runs. It is bound to return you the optimal given the current problem solution. It's not in that way. It's not a Monte Carlo algorithm where that it will come back within some fixed time. If the solution is like much complex and it requires like traversing the whole space, it will do that. So it is going to guarantee you that it's going to give you the optimal solutions. Does that answer your question, Oman? Perfect. Cool. So let me just go back to my thing. So yeah, I think we were yeah. So this is one of the solution that we have, and the crux of the thing that we did here was that like we actually took that problem and we defined the problem in terms of an optimization objective, and we also defined what are the constraints that we're operating with, and then we use the OR tool library to specify the problem and like just specify the constraint and the objective into this into the OR language, and then use it to solve the problem. So I think that's the beauty of this kind of solutions, is that like we sort of still take the seat of the formulating the mathematical optimization and let the solver solve it. And for most of the interesting problems, we have good solutions available. But at this juncture, I also want to call it out that like, although one of the caveat that goes with this formulation is that like, Mathematical optimization is invariably, specifically in this zone, is invariably ridden with problems which are all NP complete or NP hard. When we say NP complete, NP complete or NP hard, it basically means that the actual solutions will be exponential, like their exponential complexity, and hence sometimes the solution is not even feasible, and sometimes the solutions are like approximate. And that's where what has happened is that over like last 50 years of research, we have identified some very fixed forms of mathematical problems. So one of those forms is linear optimization. So when we talk about these fixed forms, like which are very specific forms of problem formulations, it also guarantees that there are like like completely accurate algorithms and so on. Yeah, I will share the material for this session. Okay, so the second question is from Bal Subramaniam. Yeah. So in case of second or third or fourth degree polynomial. Okay. So cool. I think the moment you start going to second, third or fourth degree polynomial, we have to go for quadratic and even more complex optimizations. Note that like third degree or fourth degree polynomial, it becomes really complex to optimize it, and they are like computationally very expensive. So typically what we do is that like if you firstly we try to go ahead for so by the way, Oscar, I'm going to share all these things. It's just that I was like I was not, I didn't know how to share it right now, but otherwise I will share all of these things. So don't worry about that part, both the slides and the what you call Jupyter notebook. Yeah. Coming back to Bala's question. So in case of if you go for this quadratic kind of function, so if it's like quadratic objective, we have solvers available, which are called as quadratic programming. And one of the very celebrated example of the quadratic programming is like SVM optimizer. So SVM support vector machines that we solve in your machine learning is actually quadratic optimized, quadratic objective and linear what you call as constraints. Even higher degree polynomials, what we typically do is that like if it's like fourth degree what you call optimization, it is objective, it's like super complex what you call as objective, and technically we avoid them. So usually if you're getting a third or a fourth degree thing, we just have to think about, is it your variables that are coming into picture? Like if it's a variable, then you can still pose it as a linear combination of variables which are third degree or fourth degree of the. So for example, if it's x, right, so you can still treat, like if it's like x plus x square plus x cube plus x4 kind of thing, you can still treat that, okay, I don't want to play around with the degrees, so I will just assume there are four variables which are x1, x2, x3, x4, such that xi is equals to x to the power that power, like it's that component. So it's like what you call as like mixing polynomials, but so the function will still be linear. So you have a linear objective, which is like x1 plus x2 plus this lambda1 x1 plus lambda2 x2 plus lambda3 x3 and so on, where x2 can be squared and x3 can be cubed. If your objective is naturally fourth degree, there are like the standard linear programming and these things don't work. You might have to go for more approximate what you call as optimization there. But you have to think about, like, because the fourth degree polynomial as an objective is rarely encountered. Like typically we don't encounter it. Hopefully that answers your question. So let's just come back to, the linear optimization. So I think we want to discuss about what does linear optimization mean. So there are three things that is happening up here. Number one, the variables. So we are saying that variables are always continuous. That's one of the fundamental thing. If the variables are not continuous, this becomes like really complex problem. And why that's happened? Because it becomes like a combinatorial optimization. And the thing is that this continuity factor is something which is not well appreciated, but it has like tremendous benefit in optimization. So what does continuity means? Continuity means that if you have a variable x and you are in a region, like you just say x plus small value, like x was 1, and then you consider a value for that function for x equals to 1.01. If the function is continuous, you can make some assumptions that the value in the neighborhood will not be too different from value at x equals to 1. So if value at x equals to 1 is suboptimal, And I have some, like, I can make some reasonable assumptions about what will happen at x equals to 1.01. So with this assumption, I can optimize things. I can actually say that, okay, if x equals to 1, if the function is decreasing function, and if x equals to 1, it has some value, I can have some reasonable judgment about where the next nearby value will be. And I may not even have to evaluate that function. So if you think about this whole optimization, you are doing nothing. You are actually just taking a big loop, a big for loop across all the variables. Like it's a nested for loop, and you're just iterating and generating a values and iterating and evaluating the function, whether what's the value, and keeping the maximum. This is the naive way of implementing it. But with all this continuity and all those things, what we have figured out that there are better ways of doing it. Like we can actually evaluate the differential and say, okay, what's the rate of growth of the function and which direction you should go ahead, and so on. A similar thing happens even in your neural networks when you do solve this SGDs and so on. That's a similar kind of thing. So that's the underlying thing. So that's where variables being continuous is a very good benefit that we have. Number two, the constraints have to be linear. So when we say constraints have to be linear, what it means is that whenever you solve this linear problem, you can actually represent the constraint by straight lines. So the moment you put straight lines, you have nice properties that you can define convex hulls. You can say that, okay, if x is one of the constraints is x should be greater than 0, the second constraint is x should be greater than 100. So you know that there are two parallel lines, which is x equals to 0 and x equals to 100, and the solution space will be between them. Now you say y is equals to 1. Y should be greater than 1 and y should be less than 10. So you know there are two horizontal lines which are parallel horizontal lines, which restrict the thing. So you can be very sure that the solution lies in the rectangle. And you can further be sure, because it's a linear optimization, that the solution will lie at the vertices of the rectangle. Now, people who are interested in knowing why that is so, I can actually connect them offline. But basically, say that the solution lies at the convex hull. So instead of evaluating every point in the rectangle, you can now just evaluate the points of the 4 points of the rectangle, which becomes much simpler. And to ensure that this happens, the third thing which is super critical is like objective function is linear. So if the objective function is not linear, what does it mean? It means that your objective can actually make huge strides. Like for example, it can actually go arbitrarily big and small if the function is not if the function is not linear. So for example, let's assume it's a 10h function. There can be sudden jumps, very spiky jumps in the function for a small change in the value of x. So those functions again violate the principle, violate the conclusion that solutions are going to lie at the convex hull. So that's why it's very super critical for linear optimization to actually have constraints and objective both to be linear. Now, the strength of this method is that it's super efficient. Like these are one of the most efficient algorithms, and they are like sort of in linear in the input variables and so on. So one question that Bala was asking, right? Like if suppose you don't have something which is linear, so the computational complexity of linear optimization is so lucrative that people actually go ahead and solve. Like in fact, even if it wants, they will actually pose the problem forcibly into the linear function, because now we know that it's a stable solution available. So let's just go into another problem, which is very common in nowadays. So everybody is influencer today. So let's assume I am a social network and I have M influencers. So they don't exist on my platform, and I want to incentivize them to basically create content for me. So now what happens is that like each influencer, we have, sorry, there's a typo. It's not M, yeah, the M and N. So there's like M influencers and N for say Nigeria categories. So each influencer can generate content over N categories. Now, what we want, we also know that we don't want too much content in each category. So we want minimum content in each category, but also maximum. So we don't want to take share chat and like make it like a bhakti channel or a devotional channel. So we want it to have like say maybe X percentage of content, maybe from devotional, from Bollywood, from movies, sports, and so on. So we want to have min max on the content that each category needs to be generated. The crux here is that like we need to pay some cost to the creator. So every time we want to engage a creator, we need to pay a cost there. And then what we want to do is that we want to solve a problem that how do you create a combination of creators. So again, I have posed this problem. So let's just focus on the left-hand side firstly. So we will again solve this through Python code base. So what we're trying to say is that like we have C0, C1, C2, and C3. These are 4 creators that I have. and T1, T2, T3, T4 are like type of content they can generate. So what it says is that C0 can generate uh, 6 units of content of type T1, 10 units of content of type T2, and so on. And we also have things like what is the minimum content I want to get from C0, and what's the maximum I can get from C0. So that's a kind of constraint that business has given to me. And the cost is associated, which is like, what is the cost that I get for actually taking this creator. Similarly, I have vertically, if you go down, deep down in the T1 column, it says that whatever the minimum number of type I need. So I need to have, like, so that my audience can engage with me, I need to have at least 50 units of T1, but I don't want to have more than 154 units of T1. So this is basically a setup. Okay. Perfect. Awesome. So I think, Bala, one of the things, right? So I think there are two things that we are talking up here. So when we actually talk about neural networks, note that like neural networks have the Adam and those things that we do there. They do not guarantee you the optimal. It's a Monte Carlo algorithm, which is that's why like epochs and X number of epochs and so on. So it's not guaranteeing any kind of optimization per se. The optimization that I am talking about, these are all optimizers which will actually converge and give you a solution out of it. So that's the first difference there. Number two, what you said, which is actually very true, and that's what I said in the beginning of my talk, that these optimizer OR tools and so on, they are great because they give you initial solution or initial proof of concept. And if you feel that it can actually answer your questions, and you want to literally go to like a billion or a trillion kind of firstly, like 1 trillion parameters and so on cannot be solved from. I don't think that even the CPLEX or even the best available solvers can solve it. I think the largest LP problem that is solved is, I think, with a million constraints, and I think a million constraints. That's what I remember. It's like for much larger problem than this, I think the computationally don't have any solutions available. In that case, we need to go for something like a more approximate solution, and neural networks are just one another way to do that optimization. So if you think about it, what we are talking is like they're exact optimizers. If the exact optimizer don't work, you go for an approximate optimizer. Neural network is one of them. It can be neural networks, it can be genetic algorithms, it can be simulated annealing. So a bunch of those things can happen, but those are more approximate algorithms. Today the talk is more about the exact what you call it, optimizers. I hope that answers your question. Perfect. Cool. So yeah, so coming back to this influencer part of it. So we also have this what you call as constraints on various type of content. Now, I think if you look at this problem, right, it is invariably complex in its beast right now. And I think that's where again if we just start thinking from our perspective, right, the way we thought about it, I think we can simplify it very easily. So let's just focus on what are the variables here. So here there's no variable as in terms of cost. So creator cost is freezed. There is no variable in terms of min or max engagement that you want to drive from a creator, like how many times you want to, how many days you want to engage them and so on. There is no constraint, there's no variable in terms of like the minimum max of a type of a content that is required. So I think if you think about it, the only variables that exist is basically how many days or how many times you want to engage a creator. So basically what we say is that, like, let's assume there is a creator which is like we denote these variables f0, f1, f2, and f3 to be number of times we engage c0, c1, c2, c3. Every time we engage c0, we get 6 units of t1, 10 units of t2, 5 units of t3, 2 units of t4, and cost is 9,000. And f0 has to be minimum 7, and f0 can go beyond 17. Now, astute readers here or astute listeners here will identify that the engagement with the creator is actually an integer variable. and what I'm using here is a real number. Now that happens because if I go by an integer program, it's much more complex and it's much more intractable than going by a linear program. And hence I assume it to be a linear, and that's where I connected back to one of the question that's I think Omar asked, which is the sensitivity. So this will become very critical in this case, because when I'm actually taking an integer and I'm relaxing it to a fractional number, it may happen that the solution says that consume 1.2 of C0, but I will either consume 1 or 2. And hence, if the solution is very sensitive, changing 1.2 to 1 or 2 will actually make it completely worse. And then we have to like repeat that, like we have to study the sensitivity of the solution and then take a call, like whether can I go 1 or 2, or shall I change the program itself. But coming back to this, so variables are F0, F1, F2, and F3. Now, one of the things that we want to do as a platform is to minimize the cost. Like that's a very, currently this has a very simplistic objective, just to minimize the cost. So the cost is basically howsoever times you have engaged a particular creator and the cost incurred. So that's basically CI into FI. The CI is the cost and FI is the times you are going to engage that creator. Now, what are all the constraints? So obviously the constraints are like LI, UI are given by the min and max columns, which is corresponding to each of the creator. So we say that FI lies between the lower and upper limit. And similarly, we have some content constraints. We want to say that if I want to restrict the number of content content units in the system, so that's what is AJ and BJ, which is represented by min and max rows. So the quantity which is there is like, which is NGI, which says that like for the jth unit, when I'm actually taking the ith creator for the jth unit, what is the NJI is actually the type of content that the creator I produces for the jth type of content. So the NJI is again given based on this matrix. So for example, n of like 2, which is like type 2 from something C1 is basically 6. So this quantity tells us that I'm actually consuming FI of this creator, and hence I will get NJI units of the jth type. And this whole thing should be below like the min and max given for that particular content. Now that's basically the form that we have. Now let's just go back to again. Yeah. So I actually go back to something like the influencer content part of it. So the same thing, like the same table here. And we are actually talking for the variables and constraints there. Now let's come back to, I think this is, I've actually, by the way, there's this very good book I can share you, which is this code is actually based on the book and the problem posed up there. And what I did was I actually mapped it to the problem in the ad space. So basically what we're trying to do here is that like, this is our solver. Now this new solver is nothing just but a function that we have kept up here. And we just say that whether if you want to go for a integer programming or a linear programming. So in this case, we by default, we don't go for a integer programming, and we typically pick up the linear programming, but the same thing can be used for integer programming as well. So we want to just say that this is my solver. I'm actually taking this whole matrix N. Now, if you look at this N here, right? So this is sort of the N matrix, which is given at the top. One other thing that you will note up here is that like in if you take a single row of this matrix, last 3 columns are min, max, and cost, and last 2 rows are basically min, max for that type. So that's what we have done up here. We say that from the matrix, number of influencers is basically length minus 2, which is like the last 2 rows are removed. And the number of types are basically whatever is the first row minus 3, the last 3 columns. And then what we have done is that basically we have actually extracted these few things out of this is just like basic maths, like basic manipulation. So we want to figure out like what is the minimum number of this influencer, what's the max number of influencer, what's the influencer cost, what's the min and max for the type, and so on. And now what we're trying to say is that like I'm actually adding up, like f is my function where I'm again adding variables. And what I'm trying to do is that like I'm actually taking up different variables for basically different influencers for basically providing the influencer count variables, which are F0s. 1 minute. Yeah, sorry. Yeah. So for each influencer, I'm actually provide. So this is this has to be a variable. I'm actually sorry for that. There's a typo here. But what I'm trying to do is that for each influencer, I have taken the minimum and max that is allowed for it, and that's how I'm creating this f variables, which is f0 to f1 with the limits of minimum and max. Now what I'm trying to do is that like I'm actually specifying the second. So this was the constraint I've specified. Now I'm specifying the second constant, which is saying that the type min, which is um, the current minimum value, like wherever the type min is the corresponding for the jth thing. I'm saying that all the places where this particular type has been used based on the FIs that is there. I'm saying that it has to be lower than the minimum of this, and similarly it has to be less than the maximum. It should be greater than the minimum and lesser than the maximum. So these are the second level of constraints which I have specified, which are from this one. Like this NGI FI should be greater than AJ, which is given from the type min. Whatever column the type min is there, and similarly the FI NIJ should be less than the type max column. Now, what I want to do is that I want to minimize the total cost, and this cost is again given from this, which is basically the cost and the times FI is being used. And so that's where I'm saying that it's FI into NI inf cost. Like basically you go to the ith, go to the vectors of ith, like n vector, and what you call array, go to the ith row and put out the cost of the influencer, which is like basically the same thing. So wherever this index for each of the influencer, go to the index and pull out the cost. So that's what I'm trying to do up here. And I say like I'm actually using FI units, so I have to multiply each one of them, and then I finally solve it. Now, if I just look at this function again, so this is just one simple content thing I have calculated. So if you take it, it sorts of shows me like this is the distribution. Like I have to pick up. If suppose I increase some number to be high here, like sorry. So it doesn't change as much because it's still going for the fourth creative to be maximum. Now, let me, okay. Cool. So this is one of the things that I want to demonstrate. So in this case, if you think about, right, I've actually added so let me just, okay, just let me just remember this line. Okay, so this is the line. Okay, and we run this. So this we were getting, and what it tells us that maximum unit of you can actually get is from, like, for satisfying other things, the maximum unit you should be consuming is from the fourth one. Now let's just take this and comment this out, and I actually increase this arbitrarily. So I sort of make it like, okay, whenever I'm using this and I'm actually consuming higher volume of um, mm, this type T1. Now, note that, right? I actually cannot satisfy, like I'm like, in order, this particular creator is producing the type 1 too much. And ideally, what happens that I can actually take at max 5 units. If you think about it, this is like 5 units is something like 1100. So I can use only 5 units of this. But because that will just make this content ahead. Like if I take 5 units of fourth, I will actually sort of exhaust this one, and then none of them can be taken. If I don't take the fourth one, others one cannot actually meet the minimum of given these things based on their maximum limit. So if you, for example, this is 360 and so on, so they cannot sort of meet everything from this thing. So if you take this scenario and run the equation, it actually gives us the no solution, because there doesn't exist a solution where you can satisfy all these things. If I do this again, it actually sorts of does this. Note that I want to minimize the cost, right? But I'm actually sort of in this zone. If I start increasing this numbers, maybe to, and say maybe 9 or say 15. So you start seeing that it is still Okay, it is still doesn't makes any difference here. We need to play around more. But I think let me just try more here. So maybe say 3. No, it is still taking 1 only. I think, am I specifying this correct? Yeah. Okay, I think I need to figure out something, but the crux of the matter here is that yes, like basically we can actually again take this problem and sort of solve this using this particular kind of optimization. Now, any question till this point? No. Okay, cool. So let's just go to the final thing. I think we have we are close to the time. So let's just go to the final thing. After this, there's one quick problem, and then I will just quickly tell that problem, and then we move forward. So I think one of the things that we can do in this kind of problem is that, like, currently what we were doing was that we are only focusing on cost. Now we can actually maximize the profit. I think in the case when the cost and profit is linearly, like they are monotonically increasing, or they're like related to each other, directly proportional to each other, maximizing profit versus maximizing cost is the same thing. However, sorry, minimizing cost is the same thing. But if the profit and costs are like differential, like the most expensive ones are not necessarily the most profitable ones, then this becomes like a sort of you have to have two objectives there. We can also have content level restrictions. So for example, we want to say that given up our engagement, we know that Bollywood content should be at least twice that of devotional content. So in that case, it's not very difficult. We have more constraint. We say that, okay, one particular kind of content has to be twice of the second kind of content. The third thing can be a bit more complex, which is like basically two influencers cannot be shown in the same feed. So now if you have content from one feed, one influencer, you cannot have content from another influencer and so on and so forth. It's not feasible in the current setup, because when we're talking about linear thing, you cannot have this engagement. Basically, you want to do an XOR gate. You want to say that content 1 is 0, then the other one has to be 1. And if it's 1 is 1, the other has to be 0 and so on. So that's where it cannot be done. And that's why we need to have like a higher degree kind of model. Now, after this, let's just move on to the final problem that I want to demonstrate here, which is around ad networks. So now what happens? You have publishers like Yahoo, MSN, and so on. They have users to whom we can show ads. We have advertisers who have inventory and they want to show ads. Now, ideally every publisher cannot talk to every advertiser. So I have a blog, I cannot reach out to every advertiser that, okay, do you want to show me an ad? And single ad network is not feasible because, for example, if it's only Google, then it's like competition is not there. So they have the complete liberty to drive the prices and so on. So obviously for this, there's a situation where we have demand side platform and there's like multiple level of agencies are there. So demand side platforms are like basically aggregators of advertisers. So advertisers come and say, fine, take my ads and show and give me the best ROI, return on investment. So the publishers say that, okay, they come to supply side platforms. They say, take my user request and then you generate me maximum revenue. So in this setup, it's basically like a complex piece of graph that exists. So we are saying that there are a lot of publishers sitting, there are a lot of advertisers sitting, and then they each one is talking to different platform, and then they want to match the ads there. Now, if you talk about in terms of like the optimization here, you can think of this as a graph. And one of the things that the variables here are like the different edges, like all the xij's that are there. There can be multiple objectives that we can talk about. So if we assume that capital N denotes the basically the nodes, S denotes the source, like basically supply, and T denotes the destination. In this case, it could be ads and so on, like basically matching publisher and advertiser. Then we can have like the first objective is trying to say that like you want to maximize all outgoing from source, like basically all the supply is being consumed. So you consume the supply as much as possible. This objective just says that maximize those edges which are taking the supply. This second objective is saying maximize everything which is like consuming the ads. Like one is consuming the users, one is consuming. So these are basically mutually same, like they are one and the same thing. You're saying like either number of opportunities on which ads are shown, you count that, or number of ads that are consumed, you count that. It's one and the same because for every opportunity, there's one ad. There can also be another objectives that we can say, for example, internally, there's an arbitrage happening. So one supply platform is selling to another supply platform. And if you want to discourage that, then this could be the third objective, which is saying that inside the node, if you're actually consuming within one internal node is giving to another internal node, we want to discourage those kind of solutions where you're saying that, okay, one supply platform is sending to another supply platform that is sending to another supply platform, and the actual ad is not delivered there. So if we go by this sort of setup, again, I think this is a slightly different formulation, again, a similar kind of thing. But in this, what we're trying to do here is that, like, now it's all about the XJ. So basically, just in the sake of time, it's like, since I'm going to share, it's the same thing. Like, we are actually taking the X and we have specified the this particular objective here. Now, just a simple example to showcase that this is happening, right? So C is one of the networks. So what I've done is that, like, C is a network that I've shown. So this is says like 0 to the other node. So it says that, like, node 0, which is on the source side, has edges from it has edges to node 1, node 2, and no edges to node 3. The node 1 has edges to node 3 and node to node 4, and node 3 has edges to node 2 has edges to. So basically saying that the source has nodes to 1 and 2. From node 1 to there is a node 3, and from node 3 to node 4. So I think there's only one path like this, which is of capacity 12, which is going there. And now if we can solve this problem, right? So we say that I want to, this is what it tells us that. So if you look at it, cool. So what it tells us that, like, the total supply that can happen from like supply to ads is actually 12. So if you think about it, from where it is coming, it's saying that passing 10 on this edge, which is here, and this 20 we can pass it on 2. And this particular thing can actually so this if you take about, right, so this 10 to 10 to 10 here, and there's an additional 2 going directly from here, which is being consumed by 12 here. So this is what this particular say. Now if I change this to maybe say 15, right, you will immediately oh sorry, yeah, you will immediately see that the supply has increased by 15 here. So what it says is that now if you take it, it says like I'm passing on this 10 to 10. Now let's assume I increase this to say 20. So I'm actually increasing this particular DSP or something has higher what you call as capacity. It doesn't matter because this node is still bounded by 10. So it only takes 10 and so on. So basically what I'm trying to say here is that, like, this whole complex problem of how do you schedule was actually again posed back in a very succinct manner in a mathematical formulation, and that we can again solve. Now let's just assume that we have we want to increase it more. We add 10 here, which is like the first node is actually directly connected to the fourth node. So again, if I do this, right, so this has suddenly increased here. So it's now saying that I can go 25 because I think this bottleneck is removed off. Okay. So just another extension to this that is feasible, right? So currently what we said is that, like, we just want to distribute the ad in the network. Now we can actually do a differential thing. For example, the cost of showing and like the cost that a supplier can get from a ad network, Facebook or Google, may be different. It can have a different weight which is associated. And if we come back to our formulation, right? So in this case, wherever there was this maximization, currently we were just using excise, we will start having a cost associated with it. And the moment you have cost, it will start, it's basically the effect of cost is that, like, basically you're saying that if something is like currently we are saying the number of impressions. Now I say that one impression is double the cost of the second one. So what it technically means, like in terms of algorithm, what it means is that the first one has increased the capacity. It has sort of become 2, and now you want to consume that capacity more. And hence it will actually drive more impression on the first one than on second one. The second one could be a guaranteed payout. So this happens, like, for example, there's a movie launch happening, and advertisers want to say that, okay, if you don't give me X number of users, I'm not going to pay you anything. And if you want to get like, if you get me million, I pay you 10 million. If you get me less than a million, I pay you 0. So again, what this means is that, like, when we have this kind of edges, like basically this particular thing, it will have constraints on the quantity, the final quantity that is coming up into J. So summation over all the T's, like for a particular T, you will sum over all these things. So like everything that is coming into a target node, and you can say that, okay, if you give me a certain number of impressions, then only I will take it, otherwise I will not take it. So you have more constraints which are added there. So this problem becomes like, it's still the same problem, but we just add more constraints up there. Cool. Okay. Yeah, so that's one thing. Okay, so I think I just want to, sorry for 5 minutes over, I just want to summarize up here. There are two things that I want to derive from this. Like, number one is that mathematical optimization provides interesting formalism for solving very interesting problem, like very in a very succinct manner. Number two, I think Google OR tools is a great package for day-to-day job, because it's actually easy to use. It's easy to integrate into your software. It's free of cost. And once it shows benefit, then we can actually start going for like more commercially powerful packages, which can actually solve much bigger problem. Note that Google OR is not going to solve, like as I think Bala was referring, right? It is not going to solve your a million what you call as constraints. It's not going to do that. It's also not going to solve like all sorts of most complex solutions. Like it cannot do many kind of MDPs and so on. But it's a good thing to start with for linear problems and so on. And many of your problems, for example, if like, I think a big chunk of you must be working in some form of feed ads, or some sort of website optimization. And I think these things can play a very good role in any of those problems. Like every of those problems, wherever there's an allocation happening, it's a portfolio allocation happening, you can always specify that as a problem between utility across different channels and then optimizing it. Yeah, cool. Any questions? If there are no questions, then the moderator, how do you want to go ahead from here?
Yeah, I'd like to know how will you be sharing the materials since the attendees are keeping on asking for that?
Sure. So I can do one thing, like I can share you I can actually share the slideshow right away. I think I can share the link. There's some way to do that, right? Okay, so that makes sense. So I can paste it right away. Yeah, so this is the link part of it. The other thing, which is okay, there is my, okay, cool. I can do this. I can save this file. I think this is self-contained. The way I've created, it's actually self-contained. I can copy this as well. 1 minute. Just a minute.
Meanwhile, I'd like to request the attendees to please fill in the poll about the feedback, as it is helpful for us to conduct more such sessions.
How can I share you the file? I have the file now. How can I share that? Can I mail? Can
Sir,
I?
yeah, like if you have downloaded this Jupyter file.
I have it downloaded.
Okay, can you send it to us through WhatsApp? Like.
Okay, I can do that. 1 minute. Or if you can share the Google Drive link here, I can just put it there.
Yeah, okay.
I got a ping. Like, can I just send it through to Prashant, right? Prashant from Analytics Vidhya.
Yeah.
Okay, let me just do that. 1 minute. Yeah, done. Yeah, I have shared him the file. Okay, so I think Lanki Kumar. Yeah. So yeah, I think there are lot and lots of research paper, and I think most of the problem, like if you read, so the way to approach this thing, right? I think it's not about approaching a paper which is talking only about optimization. In fact, every paper talks about that in optimization for that matter. So let me just give an example. This one. Cool. So let's assume this is a click prediction paper. And I think if you think about it, there's a yeah, this is the solution that's happening up here. And yeah, 1 minute. Yeah. I think this is not. I think this is sorry. I think this is not the one. But I think the thing that I'm trying to tell you is that like most of the papers that you solve with respect to your problem space will actually be talking about optimization, formulation someplace, and solving that usually will be done through this kind of solvers. And for that matter, neural network itself is like one of these solvers. Yeah, I think this is not the one. I think I forgot that paper, but it okay, it was probably. I think this was. Yeah, I think moderator, you can go ahead.
Okay, thanks a lot, Rahul. On behalf of Analytics Vidhya, I'd like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future. And the LinkedIn profile of the speaker is shared in the chat session. I hope you guys have filled in the feedback poll. If not, I request you to please fill in the poll about feedback, as it is helpful for us to conduct more sessions. And the recording of this session will be available in a few days in our YouTube channel, and the link for the same, as well as the link for upcoming few sessions, is shared in the chat session. Thank you, everyone. And if you could wait for a few more minutes, we'll be sharing the Google Drive link with the Jupyter notebook. Thank you.
It's already shared.
Okay. Thank you so much, everyone.
So yeah, I think that's one thing for Rutuja, right? I think this is the book. It's Search Crack Practical Python AI Project. So I literally the thing that I presented today, I think is first one or two or one or fifth chapter, something like that. I just picked that up, and that's the book I learned used to learn this OR tools kind of thing. There's a very good documentation on net also available, but this is one of the book, and it is pretty good in terms of like it has seven or eight chapters, and it discusses all variety of problems. Like I did a very peak view at two problems, linear program and a network program. It also has, I've already pasted that on. Yeah, so it has a look at multiple kind of problems. So that's a pretty neat book that I've seen. Yeah, that's what I want to say. Thank you.
Thank you so much for the session, Rahul.
Ernest, I think it's above the Search Crack book there. Thank you. Bye-bye.